No. Okay, recorder is on. Double check. Yes, recording. Very good. Okay, so we are on 310 right now. All right, so we are back to cisp310, and the recorder is on, the mic is on. Thank you so much for the rechargeable batteries. I will return those to you. Okay. All right. So we'll start with a homework assignment. Oh, man, homework assignment. See, my response is the same as yours because I have to grade it.
Is it going to be like the last homework kind of?
No, it's going to be here. It's called Egg Hunter because it's close to Easter, or at least last time when it was offered, it was close to Easter. If anyone feels that I should not be using religious references and stuff like that, let me know, and I will change the names of the homework assignments. But Egg Hunter by itself is not an issue, because all kinds of snakes, go egg hunting all day long.
Bunnies don't hatch out of eggs.
Sorry?
I heard something about a bunny inside an egg.
Yeah, there's a bunny too.
Bunnies don't hatch from eggs.
Unless you take a bunny, put it inside of an egg, and let it fight its way out.
What? Mad science is this.
Mad science. That's right. Okay, so we'll go to the downloads folder, and I will tar that thing. Okay, so before I go any further, okay, let me start from scratch. Okay, so the description of the homework assignment is here, but the first thing you have to do before you can do anything about the homework assignment is to download the file and move it onto the virtual machine. Remember the virtual machine? Yeah. And then you have to untar that. Okay, so I'm going to show you all the steps to do that, and I will start my very own virtual machine so I can give you the entire process of how to get this done. Okay, so I have my virtual machine already here, and I just run the shell file. You guys can double click on the batch files depending on which version of Windows you have, and that will start up the virtual machine. And in my case, it will only take a very short amount of time. In your case, it's going to be a little bit slower because you don't have the acceleration available when you're running QEMU in Windows. But it's okay, it will just take you a little bit longer to start. It's not going to be a big issue. So I have just minimized the virtual machine itself, the QEMU, the console. I don't use it anymore, okay? Instead, what I will use is SSH and SCP. Okay. All right, first thing first. I go to my downloads folder, and I want to identify the file that I have just downloaded. And there are several of these. I can remove all of them. I just removed all the files. Good thing I don't have anything of value. That's the thing about using Linux is if you run the wrong command, bad things can happen before you realize you just typed the wrong command.
What do you mean delete the main directory?
If you want something that is really bad, this is even worse. Because the -R means recursive, F means force, which means when it is attempting to delete a subfolder, it won't even prompt you and ask, hey, do you really mean that? Without the F, it will. Okay, it does ask you, you're about to delete a folder, are you sure? Then you can say, no, Control-C, get out of here. But if you put an F, it means force, so it won't ask you anymore. So this is bad if you run this and press the Enter key, so I have to be careful not to press the Enter key, and that's why I'm using my left hand to press the backspace because it is harder for my left hand to accidentally hit the Enter key. Okay, so I can re-download the file because I just want to make sure I get a fresh copy of this. So save link as, putting into the temp folder, okay. All right. So now that this is in a temp folder, I go to the temp folder, I do an ls-l hunt.tar.gz, and it is 381 bytes, okay? It's a really small file, it is compressed, and it is just an archive of a folder. I'm not going to do anything in this particular environment because I want to do everything inside the Linux virtual environment, okay? Because it's a 32-bit Linux implementation. What I have right now is a 64-bit, okay? To most of you, you can use WinSCP or FileZilla will do the same thing. Okay, let me show you what is FileZilla. How many people know what is FileZilla already? Okay, so the majority. But if you don't, that's okay. Just go to FileZilla. Just search for that. And it is an FTP client program. It is open source. You can download it, install it. It doesn't cost you anything. Okay. Let's see. Do they have a Linux version? Because if they do, I will probably install it just so that in class I can show you what it looks like. And the answer is yes, it does. So I'm going to go ahead and download this, install it, so I can show you how to move a file. Yep.
In the virtual machine, isn't there like already a little program there? It's like Win.
Yeah, you have WinSCP already. That works as well.
Yeah.
Yep. You don't have to use this one. Okay, since you guys do not seem to be particularly interested in using that one, I'm just not going to run it. Because in Linux, it's so much easier, okay? And this is what I need to do in Linux. It won't work in Windows, by the way. And forgot to specify the name of the file, and then the destination. There we go. So in Linux, I can do this using a single command line. I can copy a file from the host environment, or what is running the virtual machine, into the virtual machine. So I'm going to go ahead and explain it, because some of this will still be useful to you. This is the name of the command line program, which most of you are not going to be using. If you use Linux or a 64-bit Linux as your native environment, yes, you can use SCP. If you use Mac OS X, you can also use SCP. So it will work in any type of Unix/Linux type environment. If you use Windows, you have to use WinSCP, which will give you a GUI. The -P, this is an uppercase P, 2200 specifies the port number. You have to use port 2200 because the virtual machine is programmed, or the batch file particularly specified that port 2200 is used for SSH connections. So you have to specify port 2200. The file that I'm transferring is called 800.tar.gz, which is on the local machine, the machine that I'm interacting with right now at this point. And then this specifies where is the destination. So in this case, the destination is specified by first the username at, and then the host name or an IP address. Localhost is fine, okay, because your virtual machine is running on the very same machine that you're interacting with at that point. The colon separates the username and the host name from the path that you want to specify. And what is following the colon is not a minus, it's not a dash, it is the tilde symbol. The tilde symbol represents the home folder. So I'm copying a file from where I am at this point. The file is called 800.tar.gz. I'm copying that to the home folder of the user in the virtual machine. Is that okay? And I'm going through port 2200 to do it. Is that okay? Sort of? Okay. And press the enter key. It will, if the connection is successful, which means your virtual machine is actually up and running, it will ask you for the password. And I think the password is live. No, it's user. I keep forgetting the user password. So the password is user unless you have changed it in your virtual machine. And if it is successful, it will just show me that it has transferred the file. Do we have any questions about transferring the file over to the virtual machine? No questions? Okay. Yep.
So this is FTP in Linux, basically.
It's SFTP or FTP will give you a command line, and it will, if I remember correctly, SFTP is more interactive, so you can actually move files in either direction or delete files, delete folders, and stuff like that. SCP is just copying. Okay. It's going in one direction. So now that this is all done, the next thing I do is I will log into the virtual machine. Now when I log into the virtual machine, I do have PuTTY here, so I can show you what it will look like in PuTTY. And for those of you who want to see how it looks like on the command line, I can do that as well. The host name is the same, which is localhost. The port number is 2200. In other words, we are using the same port number for transferring or copying files as well as the remote terminal, because SSH is capable of doing both. Connection type, just leave it as SSH, and you don't have to specify username and just click open. And now we have this one here. It does look really kind of awful because of the font size. Let me see if I can change the, nope, that won't change that. Ooh. Okay, but
I think you have to do it in the settings before you even log.
yeah, because in Windows it allows you to change the appearance, by right-clicking on the title bar. In Linux, that option is not presented. But basically, you can log in like this on the command line for those people who are using Mac OS X or 64-bit version of Linux. You can also just type SSH-P, but this time is lowercase, okay? So SSH as a command wants to use lowercase p to specify the port number. SCP, on the other hand, wants to use uppercase P to specify the port number, okay? If you use Windows, this does not apply to you because you'll be using PuTTY in order to do exactly the same thing. So SSH-lowercase p 2200 user at localhost, basically the same thing as SCP. Press the enter key, type in the password. Now I'm in the virtual machine. Are we still doing okay so far with this? It's really just how to copy the file over and then how to log in into the virtual machine. We have done this part already. This is more or less a reminder. Okay. So now that I'm on the virtual machine, the first thing I do is ls, which is to list the content of the home folder of user. And we do have the file egghunt.tar.gz, and the first thing we do is to decompress that file and expand and get its content. tar xzvf will do this. It's the same command that you have used in the past. Okay, so there's no real new stuff at this point. Press the enter key. It will show you what files is decompressed. So we are creating a new folder called egghunt, and in the folder egghunt, there's a single file called bunny. So you go into the folder, okay, CD or change directory allows you to change the current working directory to wherever you want to go. We just want to go into the subfolder egghunt. Press the enter key. You can do ls again if you want to. It will just show you that we have a file bunny.s. So we can use your favorite editor. Mine is VI. You don't have to use VI. You can use Nano. And we say, VI bunny.s. Press the enter key. And this is the content of that text file. This is just a text file. Are there any questions about getting into the text file itself? No questions? Okay, all right. Okay, so the next thing we want to do, that I want to do, is to show you alternatives of using, of which editor you can actually use. So what I'll do, I cannot show that. WinSCP has its own editor, so for those of you who know this, okay, you can right-click on the file on the remote side, and it will give you an option of editing that file using the built-in editor, text editor of WinSCP. So if you absolutely do not want to learn a new editor like Nano or VI, you can do it that way. Is that okay? Has anyone tried that using WinSCP? Yep. Okay. Does it work okay? Yeah. Okay. All right. So that's one way to do it. All right. So now that we can get to the file, the question is, what are we doing with this particular homework assignment? So I'll explain what we are doing here. Okay. The ultimate objective is at this point the register EBX. Now, how do we know EBX is a register? Based on what we have already talked about on Tuesday. Yes? The percent. The percent symbol, very good. So the percent symbol is a universal prefix of registers. So whenever you see a name that has a percent symbol in front of it, it is a register. So in this case, well, I think last time I also mentioned that EBX, ECX, and EDX are all registers, right? Okay, so we know that EBX is a register. So at this point of execution, after the move B instruction, right, above this one, I want EBX to have the value of base 10, 385,880,604. Exactly. I don't want it to be one off. Is that okay? Does everybody understand the objective of this homework assignment. Yep.
So we should change that to base 16 or base 2.
I'll leave you guys to figure that part out, okay? Because but you're on the right track, okay? I'll tell you that you're on the right track because you have to look at you have to look at EBX not in base 10. Okay. In this class, when I say not in base 10, I think that pretty much give you the answer already. Okay.
So the base 2 or base 16?
Maybe I meant base 17.
That's what I thought personally.
Yeah, we just need a G to be put that one additional letter, right? And we can use base 17. And 17 is a prime number. I like prime numbers. They're really useful. Okay, so that's your objective. So now the question is, how do we do that? The first instruction is something that is already familiar because we talked about this one already. The first operand, or the first thing right after move L, starts with a dollar symbol. And can anyone remember, any type of operand that starts with a dollar symbol is called what?
Constant.
Constant is one, okay? It's also called an immediate operand, okay? You can call it an immediate operand, you can call it a constant, but basically whatever you specify as the underscore, let me show you the underscore here. So whatever you specify as the underscore will become the new value of the entire EAX. Is that okay? So this one is pretty simple. The next instruction is a little bit awkward. We haven't really talked about this instruction yet. So instead of just giving you the description of this particular instruction of what it is doing, what I'll do is I'll do the same thing as last time. First of all, erase stuff from the previous class, or just enough of it, and I would use the C notation to denote what we're doing with this instruction. Without even explaining it, can someone identify which one is my destination? Which one is storing? The second one, very good, EBX. So in this case, we have EBX being the thing that is being changed. It is overwritten. It is overwritten by the reference, and then we have EAX here. In other words, what we are doing is we are looking at the register EAX and say, I don't want to copy just whatever is in EAX into EBX. I want to use EAX as an address. Go to that location, and then we copy whatever is at that location into EBX. Is that okay? And that's why I use a dereference symbol here, because we are not copying EAX to EBX, we are copying what EAX points to EBX. Yep.
Are there parentheses required?
You mean that one in the assembly code? Yes. In the assembly code, the parentheses are required because this is how you indicate that you want to use EAX as an address. The first operand is called an indirect operand. Okay, this is an indirect operand. All right. So remember how last time we used the logic sim to illustrate, how things are really happening? I'm going to do exactly the same thing here. So we'll go ahead and start up logic sim. And I'll pre-program, I'll change the RAM content a little bit. This is the wrong one. Oh, because I didn't specify which file I want to open. That's processor. V2. Oh, we wanted one under 15. There we go. All right. So what we'll do is I'm going to hack the content in the registers a little bit and hack the content in RAM a little bit. So we go to the RAM locations here. I'll just randomly pick one RAM location. Let's pick this one here. Okay. This is RAM location 05. Okay. I'll change the content of this location to some specific value. Let's call, let's make this E2, okay? So the content of location 5 is now E2. I don't want it to be 0 because everything is 0 to begin with. I just wanted to start with a particular value. And then I go to my registers. Okay, so switch to my register bank and show the content in the register bank. I'll just pick 2 random registers to work with. So I'll pick register 5 as the one that is supplying the address. So I have to put a 05 here, okay, because I want to illustrate that specific instruction. I don't want to illustrate how we get the 05 here. And we'll also specify some garbage content in register 1, and we'll just specify 8D in register 1. So what I want to do, if you want to write down so they can supplement, well, suppose I can just use my text editor here to document what I'm doing. Just hold on a second. Okay, so what I want to do here is I want to do something that is about the same thing as move and then indirect. In our logic sim, we refer to registers by number. So in this case, we are copying whatever register 4 points to the destination. So this is register 4, and we want the byte at the location pointed to by register 4 and copy that to register 1. This is what we want to do. Are there any questions about the parallelism between this made-up instruction as opposed to the instruction that I'm trying to explain in the homework assignment? No questions? Okay. It's just that with our simulator, I use R0 to R7 to refer to the registers. In the i386 architecture, they're named EAX, EBX, ECX, and so on. But I'm trying to use exactly the same syntax. Okay. All right. This is what I want to do, and this is how you can attach comment to a line of code in assembly. You start with a pound symbol. Everything to the right-hand side of the pound symbol to the end of the line will be ignored by the assembler. So you can type whatever you want. So what I'll do is I'm going to say R1 equals to dereference R4. In other words, I use R4 to specify an address. I go to that location, copy whatever is at that location into R1. Is that okay? This is a complete parallelism to what we are doing with the actual i386 architecture. Okay? All right. So now that I have documented what I'm trying to do in LogicSim, we'll go ahead and do it. Okay, so getting back to the main here, I have already put in all the values that I need. What is the first thing I need to do? When you have a move instruction, the first thing you need to do is to get to the source, okay? The source has something to do with register 5, R5, but it's not exactly R5, but we still want to get R5, and we want it to drive which bus. Every time you specify a register, you have to ask, the first question is it an input or is it an output? And then the second question is, if it is an output, what is it driving? What do you want it to drive eventually? So let's answer that first question first. Is R5 an input or an output in this operation? It's an output, okay? It specifies something. It is not getting changed. If it is an output, what it is trying to, what should it be driving? What do you think? Okay, so let me just repeat it here. R1 equals to the referencing R5. Okay? So R5 is specifying a memory location. Which bus specifies the location that you want to access in the RAM module? The address bus. Very good. Okay? So we go to the RAM module here, and then we look at the address bus, which is this one here. And then we look at the register bank, and the register bank has 2 outputs. This is the first output, this is the second output. And you can already see which one can potentially drive the address bus. It's the one that's being selected here. This bus does not drive the address bus directly, but it does go through a MUX, a multiplexer, that can connect the highlighted line to the address bus to connect these 2 together. So the question now is, how do I specify the address driver select pin to make that connection happen? So what you do is you count the this is input 0, this is input 1. So we want input 1 to connect to the output of this particular multiplexer, so we specify 0, 1 here. Are there any questions about how we specify the multiplexer so that the output of one of the outputs of the register bank is now driving the address bus? Is that okay? All right. But nothing is really driving yet, because if I click on the address bus, it will still show that, hey, nobody is driving this bus. What is missing? Let me scroll a little bit to the register bank. Okay, this is, no one is driving here because nobody is driving here either. If nobody is driving there, that means this output of the register bank is not outputting anything. And why is that the case? There's a output enable that we have not specified. So the output enable, this is register 1 output, so we have to enable this one first. Then we look at this line and go like, okay, something is driving it, but it's not the right thing. Because which register have I just selected as the output?
0.
Register 0, because reg1 out cell is the selector of which register is outputting to port 1 of the register bank. Which one do we want? 5, right? And 5 in binary is 1, 0, 1. Okay, so we specify 1, 0, 1 here. And then check again the content of the output. Okay, did I make a mistake?
It's the register 4.
So it's,
I put it in the wrong register?
yeah.
Okay.
Circuit 4.
I have to fix that. And also fix my notes here. Oh, that one is right. Okay, I wonder where I make that mistake and think it's register 5.
Since we do start at 0, if you're counting, it would technically be 5, and lost in translation.
Maybe, in somewhere in here. Okay, so now that we specify the right register, let's double check. Okay, 0, 5, that's the right thing, okay. And we want to look at the RAM module and say, okay, are we addressing the right location? Oh, no, nothing is being addressed right now. What is going on?
RAM select isn't it?
RAM select is not on, and also we haven't specified the operation. So we want to specify that this is going to be a read operation first. And then we specify that this is in fact the RAM module that we want to use, and now it is being addressed. Are there any questions at this point? A lot of this stuff that we have done already, it's just, we'll keep doing this over and over again, and then we'll become more and more familiar with how to tweak the various pins to get certain things done. Then we can make the drum of the music box. Okay. All right. So now that we have specified location 0, 5, and this is a read operation, the data bus is going to output the correct data. Okay, let me click here. It says right here it is 1110, 0010. Is that the right output? E in hexadecimal is 1110 because it's 14, and then 2 is 0010. So we are in fact addressing the right location, and it is presenting the data onto the data bus. What do we want to do about this content, the E2? Oh, we want to store it into register 1. So now we trace the data bus. We trace the highlighted line, and it is going almost all the way back to the register bank, but not quite, because it has to go through this mux here. This is input 0 of the mux, and the mux has the selection specifying the input 0 already. So that means we are already switching to the right input. So if I click here, it should give me the same result because it is already on the right track. Okay. So we have everything here. We have to now say, okay, but which register do we want to be changed? We want register 1 to be changed. So register input selection has to be changed to 001 to specify which register is getting the new content. And then we have to enable the input so that we can tell the register bank and say, yes, I intend to change one of the registers. And then what do we need to do? The clock, very good, because it is a rising edge sensitive register. So we change the clock to 1, change it back to 0. We go to the we go to the register bank, and then we look at register 1. In fact, it has the content of E2, which is the same content at memory location 5, and 5 is stored in register 4, which is used as the address. Are we doing okay so far with what I just did in LogicSim? Because all of that is really just to illustrate what that one instruction is doing in your homework assignment. Is that okay? All right. And before we move on, because I saw people taking pictures, I just want to make sure that I'm still recording. Yep, okay, so that's good. Just want to make sure. All right, so we have another mystery solved in the homework assignment. So let me switch back to the right page. I think I just got out of the editor. Or too many tabs. I'm going to close off some of the ones so I don't have to keep searching for the right one. Not that one. So this one. Okay, so we have just explained, let me turn on the line numbers, so this way we can see which line we're dealing with. So I have just explained the instruction on line 10. Line 11. Line 11 is a little bit different. It is move W. And the next one is move B. Okay, so without even referring to the nodes, can someone guess, just give me your guess, what B, W, and L stand for? W is word, okay. L is long, and then B is byte. Okay, very good. How wide is a byte? How many bits are in the byte?
8.
8 bits. How many bits are in the long?
32.
32. Okay. So how many are in a word? 16. Exactly. So by specifying B, W, or L, you can specify how many bits or how many bytes you are copying from the source to the destination. Move long is copying 32 bits. Move W is copying 16 bits. Move B is going to copy 8 bits. Is that okay? All right. So if that is okay, then we have to look into this register here. We have never talked about BX as a register. We only talked about BX. Okay. So do you think BX is related to EBX? It's probably related because the names seem to be derived. The EBX seems to be derived from BX. So you're correct. They are related. In fact, BX is really just a small portion of EBX. Okay. So this is another picture that you will probably find useful throughout the semester, especially the beginning. Okay, so I'm going to use this to represent, say, EBX. Okay, so this entire thing is EBX. EBX has how many bits again?
8.
Okay, just look at how we use EBX. How many bits are in EBX? 32. It's a long register. It has 32 bits. So the way we name the bits is, this is bit 0. The least significant bit is bit 0. The most significant bit is bit 31. Is that okay? All right. BX is a window into EBX. In other words, it really is looking into the same register, but it is confining itself to say, I only want to look at the first 16 bits. So BX is really just referring to bit 0 to bit 15 of the same register EBX. So physically, there's only one register BX, or register B. EBX refers to the entire thing, 32-bit. BX is only referring to the least significant 16 bits, but it's the same physical register. We are only controlling the window that we are looking into. Yes?
So that means that X would be 0 to 7.
You're close, okay? So we can chop it up even further. So this entire thing is known as BX, but it really is just a window into the same physical register. And then we have two more ways to chop it up. Within the least significant within the least significant 16 bits, we can chop it up again into two 8-bit portions. Okay. The least significant 8-bit portion, which goes from bit 0 to bit 7, is known as BL, the low byte. Okay? And you can probably guess what the other side is. From bit 8 to bit 15 of the same physical register, it is known as
BH.
BH, the high byte. Okay, BH. Are there any questions about how we dissect the same register? There's only one register. This entire picture is only one register. It's just, how many ways can we look into the content of this register? Yes?
So if you use PHBL, you ever have to switch something else?
If you only use BL and BH, are you referring to bit 16 to bit 31?
Right.
But there's no name, there's no way to refer to these 16 bits individually. Okay? Are there any questions about this part? Yep, go ahead.
To use BH, you have to have used BL.
No. You can, the only requirement is the width specification of the instruction, like your move B, the move W, or the move L, that has to agree with the width of the register that you specify. So when you say move L, you better make sure you're using the EBX, EAX, ECX, or EDX. When you use move W, you have to refer to just BX, AX, CX, or DX. When you use move B, then you have to refer to the L or the H. Any other questions? Okay, so what follows is kind of important. I think it is kind of important. Some people will say, I know this already, which is great. Some people may not, have these ideas, so it may be something that is useful to you. After I have what I have just said here, what do you do? Do you just take my words for it?
Yeah.
If the answer is yes, that means you have never taken another class from me before. See, these guys are smart and they say, no, I don't take your words for it. Not that I try to intentionally lie or mislead you, but sometimes I make mistakes. So how do you double check and say that, okay, now I understand these words? How do you check it? Well, the way you do it is you use a debugger. So what I'll do is I'm going to get out of this particular program for a little bit, okay? I'm going to go to a program here. I'll just call this test1.s. Okay? In other words, I'm just writing a very tiny little program to test the theory of how we chop up a 32-bit register into individual and smaller parts, just so that I can confirm my understanding is correct. Okay? So I will design this particular program. This is also a good opportunity to make sure that I know how to write a program. We start with .global _start colon to define the actual start label, and then we can specify the instruction. So the first thing I want to do is something that we have done already. We use move immediate, which is a constant, but I'm being careful about what type of constant I'm copying to a register. So I will specify something that has no repeating pattern, so I can clearly, easily see what I'm copying over. So I will do maybe 4, 8, 2, 1. Okay, there we go. So this is a 32-bit constant in hexadecimal. I know this is a hexadecimal number because it starts with 0x. Okay, 0x in C also, C and C++ and Java and most programming languages is the prefix of a base 16 number or hexadecimal number. This is a base 16 number. How many bytes have I just specified? Each hexadecimal digit specifies how many bits?
4 bits.
4 bits. And how many digits do I have in this hexadecimal number? Not counting the prefix. 8.
64 bits.
So, no, 8 times 4 is
Oh, wait.
32. Very good. So I have just specified a particular bit pattern that is a 32-bit bit pattern. And I put it into a register, a 32-bit register, let's say EAX. This may also be a good time for you guys to experiment and find out, but what if I give it the wrong type of register? What if I give it a 16-bit register? What is it going to do? well, the assembler is going to complain and say, hey, you cannot do this, okay? But you might want to, just try out different things like this, just so that you know what type of error message you can expect when you know the nature of the problem. Because later on, when you see the message, then you can immediately tell, oh, okay, I know this error, I know how to fix it. Okay, so this is the first instruction. The second instruction is a move W instruction, okay? So we'll go ahead and copy another bit pattern, 16-bit this time. We'll just use something easier, 1, 2, 3, 4, into AX, okay? The theory is, if I do something like this, then the most significant 16-bit of EAX should remain unmodified, while the least significant 16-bit is changed to 1, 2, 3, 4 in hexadecimal. Is that making any sense? So I can check, I can double check whether that is true or not. Okay. After this instruction, I'm going to move to another one, which is just a move byte instruction. And this time I will try something even simpler. Okay, put a 0 into AH, not AL, but AH. So this will only change bit 8 to bit 15, which is right in the middle of the entire 32-bit register. So that byte, okay, those 8 bits within the 32-bit register should be the only portion that is zeroed out. Everything else should remain exactly the same as before. Are we doing okay so far with this code? Okay, all right. And then what we'll do is we'll give it one extra instruction just so that I can track down things without crashing the program. No NOP stands for no op. It doesn't do anything. It just gives me a place so I can stop. All right, so this is my test program. I exit out of the editor, and then the steps to do this. This is the first time we do it, so we are going to spend some time to talk about this part. Okay, and I will hide the other one because it's scrolling and it's really distracting. Okay, so this is the command to assemble a particular assembly language program. And I'll explain the various parts just so that you know which part is doing what. The name of the command is AS for assembly, or for assembler. This part specifies that I want to include symbol table into the object file. In other words, I want to be able to debug this program in GDB, and that's why I need this option to include the symbol table into the object file. -O is specifying, okay, what is the name of the output, which in this case is the object file. So the object file doesn't have to be test1.0. I could have named it, ASDF.O or just ASDF. Okay, the extension is optional. Okay, you don't need to specify .o as an extension, but it's just conventional that I would use the same name as the source file, which is test1, which I have a title later on that will fix. And then the .o with a lowercase o is a convention of an object file. Okay. So once again, this is just a convention. You don't have to follow the same naming convention, but it really helps if you have a habit and you are following the same convention. The last part, let me just highlight it now. The last part specifies the actual name of the source file, which is the text file that we have just edited. Okay? So as a whole command, this is assembling the source file, test1.lowercase(s), into the object file called test1.o with a lowercase o. Are there any questions about what this command is about to do? Or any of those terms? What is an object file? In your previous class, cisp310, I think those terms should be mentioned at least, okay? So, but not every professor is going to mention those terms. So does anyone want me to explain those terms? What is an object file? Okay, all right, so I can explain an object file. All right, but first of all, let me just run the command. Okay, first of all, this is called the source file. Does everybody understand what is a source file? Who reads a source file? It is intended for whom?
Program.
The programmer, the person who's writing the program, and also the assembler in this case. Okay, but the content is easy for us to read for the most part because that's the whole idea of a source file. An object file is a binary file. And the only way to really look into a binary file is obj dump or object dump. Okay? If I do an obj dump dash D of test1.0, which is the file that I have just created. This is the result, okay? In other words, what it does is it will translate the code that I specified in the source file. I hope you guys remember this part here, right? This is what I specified in the source file. Now it is taking away the L and the W and the B because they can be implied. So there's no need to include the suffix. But the assembler is the translator that translates the instruction or the instruction in text in the source file into the binary format that the processor understands. So when you look at this part here, B821A4AEDF2, that specifies the instruction, a 5-byte instruction that your Intel processor can read in and execute and ends up copying F2ED4A21 into register EAX. Yep.
All right, so, this is basically a two-part question.
Go ahead. I like two-parters.
So basically, like this. So basically, the line is like how the bytes are stacked up in memory, right? Like.
Correct. This is a portion of the object file, which is the binary code corresponding to the instructions that we specified in text.
And the other question is the one furthest to the right. Is that the lower address or the higher address?
Aha. Well, that's a good question. Let's go back to that question a little bit. So the question is, what is this F2 and what is this ED? They sound awfully familiar because, hey, the same things are over here. So the question is, what is the F2? The F2 refers to the most significant byte or the least significant byte? What do you think? The most significant byte. So how come things are kind of like, they're spelled sort of backwards? Why is that the case? We explained that concept in the previous class. Sorry? Because it is little endian, which means the least significant byte is stored first with a lower address.
So like basically that's how it's pushed on the stack with the B8?
No, that's nothing to do with the stack, okay? It is just how it is arranged in memory. So what this means is at location memory 0, we have a B8. At location 1, we have a 2-1. At location 2, we have a 4A. Location 3, we have an ED. Location 4, we have an F2. That is the sequence of how the bytes are stored when we run this program in memory. Is that okay?
Yeah, I think I just have my definition for little endian, big endian.
Rest assured, this is not the result of someone being dyslexic. Unless you count a computer being dyslexic.
So like in this case, the most significant bit is in fact on the highest, like at the higher.
Yes, the most significant byte has the highest address. Because F2 has an address of 4, whereas 2-1 has an address of 1.
And this is little endian or big endian?
This is little endian, which means least significant byte stored lowest, at the lowest location. Okay? Any questions about this? What about a B8? What do you think a B8 is? Because we don't have the constant B8. This is the actual opcode. Okay? B8 being 11011000 is the actual bit pattern that tells the processor the following. We are going to modify EAX. And whatever is the other 4 bytes within this 5-byte instruction specifies the constant that we're copying. Is that okay? Yes? No? It's good? Okay. The next instruction is kind of the same thing because we can see that we are copying the hexadecimal number 1, 2, 3, 4 into AX, and we can certainly find 1, 2, 3, 4 here. They are in this particular order because of little endian. But this time we have, hey, what is going on here? We have 66B8. Those two combined is now our opcode. And you can see that, hey, but why is it using B8 again? That's because B8 is the move instruction. In 32-bit mode, when you just say move, it automatically defaults to 32-bit move. if you want to specify 16-bit move, you have to use a modifier. The 6.6 is the modifier to say that, oh, use the 16-bit version of the following instruction. So the 6.6 is really just saying, okay, it's not a 32-bit move, it is now a 16-bit move. Okay? But combined, these 2 bytes, these 16 bits, specify that we are changing the least significant 16 bits of EAX. And the B400 is the next one. We're just copying over bit 8 to bit 15 of the same register. Are we doing okay so far? But remember, the context of looking at this thing here is just to say, okay, what is the assembler doing? The assembler is doing just that. It is translating the instructions that we have written in text into binary format that the processor understands. Is that okay? So that means the program can be run at this point, right? Because it's already in binary format that the processor understands. There's one more step. Yeah, go ahead.
Since we're in the virtual, what memory is it using, and what's in that memory already?
Well, that's a good question, because we don't really go to location 0. Location 0 is not one of the locations that a normal process, a normal program in execution can access. Okay? So we're not done yet. Okay? We cannot run this file as a .o or as an object file. Okay? The question is, what is missing? What else do we need to do? Yes, go ahead.
Okay, so you know how with C and C++ you can overload a string and then you'll have a problem? With this, can you do something with the code that you'll pretty much, fry a register inside of your processor or something weird like that?
Well, unless Intel makes a really terrible mistake in the design of the processor, you should not be able to do that.
Okay.
You should not be able to do physical harm to the processor by using these instructions.
But you can still pretty much overwrite some core.
Yeah, you can hose it. You can specify some really random value that does not correspond to an instruction. It will give you a probably not a segmentation fault, but it will tell you that you're trying to do something that is not okay. Yeah, the operating system itself will not crash because we are running in what we call protected mode, which means if a user program is trying to do something that is not supposed to do, the processor will inform the operating system and say, hey, this is a bad boy trying to do something bad. And then the operating system will just step in and go like, okay, you're done. And you will see that usually as a segmentation fault, but there are other faults as well corresponding to division by 0, invalid instructions and stuff like that. Okay. Okay, so what is missing? Why can't we run this file as test1.0? What is missing? Well, okay, so at this point we have one single source file, okay? And obviously this is a really small one, okay? If you look at a large project, okay, let's say we're dealing with LibreOffice, okay, which is a pretty big program. What do you think what is the complexity of that program in terms of just kilobytes or megabytes of code as the result? Hundreds of megabytes at least, okay? Are you going to specify the source file of a program that gives you hundreds of megabytes of object code in one single source file?
Or you're gonna break it up?
You will break it up. Why do you want to break it up? Why not have a single source file that has millions of source code, million lines of source code?
Modularity.
Say again?
Modularity.
Modularity, and that means what?
Break it up.
To break it up, but how do you break it up? Every 100 line into a file?
Or a function.
You group it by function, right? You group it by, what does it serve? What purpose does it serve? Are these, subroutines related, and so on? So you have a logical way to break up a program. Yes, go ahead.
I was just gonna say it's easier for the company to just split it up with groups of programmers who are targeted at working out.
Okay, so breaking up a huge program into many, many different source files makes it easier for group management, right? For source code management. That is kind of true and not true. It's true from the pragmatic perspective, because now using the name of the file, you can kind of guess what the file is going to deal with. Okay, but from the technical perspective, it is not needed. Any type of version or revision management system like Git, CVS, and so on and so forth, they can handle a single file being edited simultaneously by multiple developers, and will be able to sync all the changes without a problem. Okay, so technically speaking, the tool can do that, but from our perspective, it is much easier if we can look at the name of a file, a source file, and know what is going to be in the content of that file. Okay, so when you have multiple source files, when you assemble or when you compile, it's basically the same process. It's a translation process. So now you end up with a lot of little object files, right? Because each source file is translated into its own object file. And each one is incomplete because they can refer to things that are defined in the other files. Is that okay? So that's why the object file is not an executable, because potentially it can contain undefined references or references to something that is not defined in this particular source file. Is that okay? So that's why we need to go through the next process, which is called linking. The linker, which in this case is called LD, is the one that can combine multiple object files into one single executable. Now, in our case, it's not going to be a big deal because we only have one source file. So, it seems to be an extra step that is not needed. But when you look at any type of major projects like Linux or LibreOffice or anything that is huge, you will see the linker has hundreds, potentially hundreds of object files, not just one. Okay? But this is the real value of breaking up a project into multiple source files. I'll give you an idea. Let's go ahead and, probably don't, I can actually erase this. We finished this discussion already. Okay. So let's say you have a 1 million line project, which I would just call it can be considered a medium-large project, not even a really huge project, kind of big. You divide it, okay, into many, many little files, and each one has about 1,000 lines of source code. Is that okay? So now you have about 1,000 of these smaller files. This is just a rough estimate, okay? Don't hold on to exactly 1,000. It's just an order of magnitude. Okay. When you change one single file, let's say this one here, does it impact the object file that is already created for the other source files? Does not impact it, right? So when you want to bring all of these back into one single executable for this entire project, you only have to recompile 1,000 lines of code. Is that okay? Because the other files are already compiled, and you can reuse the object files from earlier recompiling. So you only have to recompile 1,000 lines out of 1 million lines. But what about the linking? You still have to link all 1,000 object files. The question now is, what is the time consumption of compiling? How does that compare to the time consumption of linking? What do you guys think?
It's going to take more time to compile.
It takes a lot more time to compile than to link. Okay. If you look into any one of your C, C++, or object-oriented programming or data structure program, okay, you see control structures, right? You see while, if, and so on and so forth. You see the use of parameters and so on and so forth. So to make a program, to emit efficient code out of your source code takes quite a bit of time. Okay, so it's a time-consuming process to compile. And yet, most of you probably will not have the experience of, this doesn't look too bad. I hit that, rebuild all button. It only takes 2 seconds to have everything rebuilt. What is the largest program that you have written?
Only a couple thousand lines.
At the most,
Yeah.
okay? A couple of thousand lines. So you don't realize how much time it takes to recompile. When you have 1 million lines to recompile, it will take a significant amount of time. Linking, on the other hand, to take all the object files and combine all of them into an executable, takes a very small amount of time by comparison. If this part takes an hour, this might take 30 seconds, maybe a minute. That's the kind of order of magnitude we're talking about. So that means if you break a large program into smaller parts, you are actually speeding up the development cycle because you are only responsible to make changes frequently in one file. So recompiling this will only take 2-3 seconds. Relinking everything may take 30 seconds, but within a minute you get everything done. If you only have one single file that is 1 million lines long, then it will take you an hour every single time you want to retest the program. Okay. Is that illustrating why we want to break up a large project into smaller files? Because there's pragmatic reason. Okay, it's not just for organization, but also because we want to speed up the cycle of development. Is that okay? All right. Okay, so now that we have a program that's ready to run, we'll run it. Now you can run it by itself, but it won't do a single thing useful because it doesn't print anything. So at this point, the only way to run a program is to go through GDB. So now I go through GDB. The first thing you can do in GDB is L for list. Okay, it will show you the source code of the program that you're trying to debug. So just L. Press the Enter key, it shows you the program. The next thing you can do is to set up a breakpoint. So to set up a breakpoint, we say B, and then we specify the line number, which is 3 in this case. Line 3 is the first line where I want to stop. So I say B3, it will stop on line 3. Then we can run the program. Just R. So now we are on line 3. It has not executed line 3 yet. Okay, it is just about to execute line 3. But it's not a bad time to take a look at register EAX. So I use IR, I space R space EAX, to look at the content of EAX. It is currently 0. Perfect. It's not that big, huge mess that I'm trying to specify. A single step. Lowercase s is single stepping, which means it will execute one line at a time. So in this case, it will execute the instruction on line 3 and no more than that. Press the Enter key. Now line 3 has just executed. What do you think I should do at this point? Let's check EAX, right? So we'll say IR EAX, and it will show you 2 numbers. The first one, the one on the left-hand side, is the same bit pattern in hexadecimal. The one on the right-hand side is the signed interpretation of the same bit pattern.
It's in what?
In base 10, signed and in base 10. But in this case, we are only interested in the hexadecimal representation, so we'll just focus on the first one. Now we are ready to execute line 4, or the instruction on line 4, which is this one here. Single step. Okay. IREAX, and what do we find? The registered EAX is almost the same as before, except for the least significant 2 bytes. Those were changed because we specifically changed AX on line 4. Is that okay? So this is confirmation that it really is, there's only one registered EAX. AX is not a different register. It is just a different part of the same register. We are specifying a smaller part of the same 32-bit register. Is that okay? Yep, go ahead.
So with line 5, no, with line.
Line 5 has not executed yet. Right? It is about to execute.
Oh, line 4. So
Line 4.
All you did there was change the 21 into 34.
No, the 4A is now 1-2, and then the 2-1 is now 3-4. It changed 16 bits, not just 8. Okay. In other words, the A4 that used to be here is now 1-2, and then the 2-1 that used to be here is now the 3-4. But that's okay. That's normal because we did ask to overwrite the least significant 2 bytes. Okay. So now we are ready to execute the instruction on line 5, which is this one here. And what do you think we should see in register EAX after this is all done?
You just change step 2 or 0 with the 34. bytes.
The 1, 2 should be changed to 0, 0. But everything else should still be the same as what we see here. Is that right? Okay. Single step, IREAX, and sure enough, only those 2 digits are changed because those 2 digits represent bit 8 to bit 15. Are we still doing okay so far with this code? Is that okay? Okay. All right. Okay, so getting back to the program that we are trying to deal with, which is bunny.s. We only have 2 more instructions to deal with, this one here and this one here. I have just explained what is bx, which is the least significant 16-bit of EBX. I have just explained what is bh, which is bit 8 to bit 15 of EBX. So now, this one that we know already, this is a move immediate, or the first operand is called an immediate operand, which is a constant, okay? Whatever you specify after the $ is whatever is going to overwrite bit 8 to bit 15 of EBX. So that one is pretty easy to explain. So the only instruction that we haven't really quite explained is this one here. We know it is moving 16-bit because it's a move W, and also because the destination is a 16-bit register, BX. But this part here has no $ in front of it. So do you guys remember, without the $, what is being done without the $?
Trying to copy the address.
Whatever you specify here is going to be an address, and then the content at that address is what is copied.
So it would be a register?
Not a register. It's a memory. You just spell out the location. You can say 5. Okay. Now that won't work, but syntactically you can do that. Okay. So let me just go here, and I can give you some ideas of what you're dealing with. You can change it to 5, which means I go to location 5 of memory, copy 2 bytes, which means location 5 and location 6 will now be copied to BX. But remember, you don't have access to location 5. It's way too low to be accessed in your program. Okay? Okay, so that means there's some other concepts that we need to explain here in order to get this done. So what we need to do is to take a look at this portion here, because this stuff we have not explained at all. I have not explained this part yet. Okay? So we'll do this one line at a time, because one line, once I explain the first line, the second line is going to be pretty easy. So I look at this line here and say, okay, but what am I telling the assembler when I spell out .byte 12, 0x12, 012? What is it really doing? .byte is called a directive. It is not an instruction. It is called a directive because it's telling the assembler to do something, but it does not actually emit instruction that we run at runtime. Okay? So, okay, fine. It's just a name. It is a directive. What is it telling the assembler to do? This is telling the assembler that we want to allocate things in bytes. Okay? The unit is a byte, and we want to make several bytes. Okay, you want several bytes. What do you want to be the content of those bytes in memory? What do you think?
12.
The first one is going to be a byte representing the value of 12, and that 12 is in base 10. If you do not see a prefix, it is in base 10. Okay, and 1, 2 has no prefix, so that's base 10. Can someone tell me right away what is 12 as a 8-bit number? Tell me the zeros and ones to represent 12 as a value.
1, 0, 1, or 1.
Okay, so that would be not 1, 0, 1, 0. That's 10.
1, 1, 2, 0.
1, 1.
No. 0, 0, 1, 1, 0.
1, 1, 0, 0. That is correct. Okay, but the whole thing is going to be 0, 0, 0, 0. There are 4 leading zeros, and then we have 1, 1, 0, 0. Okay, so that's the bit pattern this is specifying. The first 1, 2. What about 0x12? What does 0x mean? We just talked about earlier. It's hexadecimal. So this is hexadecimal 1, 2, which means what is the bit pattern that thing is specifying?
0, 0, 0, 1, 1, 0, 1. No.
No.
1,
Zero, zero,
It's
zero,
0, 0, 0, 1
one,
being the
zero,
1,
zero.
and then 0, 0, 1, 0 being the 2. Because each hexadecimal digit specifies 4 bits. Okay? What about the last one? 0, 1, 2. The 0 is in fact a prefix. It is a prefix for a base 8 number. Okay, so in this case, 0 is a prefix, and then we have 1 as one base 8 digit and 2 as another base 8 digit. Now 8 is not bad, okay? It's not as good as 16, but it's not bad. It's better than 10. Because because 8 is a blah 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 of 2. Power of 2. It is a multiple 2, but it is a power of 2. So when you have 0, 1, 2, what is the bit pattern that we are actually specifying? 0, 1, 2. The 0 is a prefix. 1, how do you represent 1 in 3 bits? 0, 0, 1. Very good. How do you represent 2 in 3 bits? 0, 1, 0. Oh, but we're missing 2 bits here on the left-hand side, padding with zeros. So this is specifying the bit pattern of 0, 0, 0, 0, 1, 0, 1, 0. Okay, now let me check whether you understand base 16 again. If I take this byte here, because it has 8 bits, what does it look like as a base 16 number? We group it by 4 again, so we have a 0 here, and then we group the other 4, and this one is an A. So it's 0A in base 16.
10, right?
Which is 10 in base 10, correct. Well, I should say 1, 0 in base 10, because 10 is the value, but 1, 0 is the representation in base 10. Is that okay? And these 3 bytes, if you have to guess, do you think these 3 bytes are scattered all over the memory, or do you think they are right next to each other? They're right next to each other. Okay, they're consecutive. Okay, there's no gap between these 3 bytes. Next question. Do you think these 3 bytes are just, as a chunk, is just anywhere in memory, or do you think it is consecutive, or it is right next to whatever is following this? It's right next to it. Okay. All right. So now that we understand what is the first line doing, what do you think the second line is doing? It says dot word.
That's gonna be what?
How? Okay, we're asking the assembler to allocate some chunks of memory. Each chunk is how long this time? 16 bits. And the first 16-bit number is going to represent the value of 34, which is a base 10 number. The second one will represent 34 in hexadecimal. The third one will represent 34 as an octal number. But each one will take up 16 bits or 2 bytes. Okay? Let me check whether you understand the concept or not. If I combine these 2 lines, okay, if I look at these 2 lines together, how many bytes will be allocated because of these 2 lines together? 9 bytes, correct. Okay, the first line will allocate 3 bytes, the second line will allocate 6 bytes, and those 9 bytes are consecutive. In other words, there's no gap between those 9 bytes. Okay? And then we have a label L1. It's the definition of a label, okay? Because we see a name of a label and a colon, it becomes the definition of a label. And then we have this thing here. What do you think is a long? How wide, how many bits is a long? 32. And so in this case, a dot long is telling the assembler that we want to allocate chunks of memory, and each chunk is 32-bit wide. Well, what values do we want to represent using these 32-bit chunks? The first one is 23 as a base 10 number. The second one is 23 as a hexadecimal number. And the last one is 23 as an octal number. But wait, hold on a second here. This doesn't make any sense because 23 only needs 1 byte to represent. So what are we going to do with the other 3 bytes? What do you think? They're all leading zeros. So those 3 other bytes, they're all zeros because we just have a whole bunch of implicit zeros before the 2, 3. Is that okay? All right. So in this case, L1 is the address of something. What is it an address of? What do you think? A label definition is always the address of whatever is immediately following the label definition. So what do you think is immediately following the label L1? Which byte, to be specific, is right after the L1?
0000 from the
It is
23
the
base
binary
time.
representation of
The 23.
the 23. Okay, so 23 as a binary number, what should it look like? So 23 is a base 10 number, right? Because I don't have any prefix. As a binary number, what does it look like?
0, 0, 1.
Okay, well, okay, how do we do this really quickly? It is 16 plus 7, okay? 16 plus 7. Now, 16 plus 7 is really important because in base 16, the least significant digit specifies how many ones I have. I have 7 ones. Okay, so we have a 7 here. The more significant digit in this hexadecimal number specifies how many 16s we have. How many 16s do we have here? We have 1. So it is a 1-7 in hexadecimal. What about looking at this as a binary number? What does it look like as a binary number? We know it is 1-7 in hexadecimal. As a binary number, what does it look like? Spell out all the zeros, all the leading zeros.
0001.
0001, which is this one here, and then followed by
0111.
0111. That's correct. Okay, so the L1 is going to be the address of this byte. What do you think follows this particular byte? Remember, I'm trying to use 32-bit chunks to represent these values. In other words, this is just one of the many bytes of the 32-bit chunk. So how many more bytes do I need to finish up one 32-bit chunk?
24 more zeros right now.
24 more zeros or 3 more bytes, and each byte is a 0. Okay, very good, good job. All right, so now that we know that stuff, and let's give it a time, we got 2 minutes. I think I can get you guys enough stuff to get this started. All right, so what we'll do is, these will not assemble because they're not finished yet. So I'm just gonna comment out everything that is not gonna work, okay? It's okay, we can just comment it out. Because my main objective is to find out what exactly is stored in memory. Is it consistent with what we just talked about? And then the second thing is, hey, what is this L1? What is the address? And I know L1 is the address of something, but which byte? And what about start? It is an address, but of which byte? So we want to figure out those things. So let's go ahead and assemble, link, and gdb run the program. There we go. And we list the program. You cannot examine the memory without running the program. So I'm going to put a breakpoint. When you specify a breakpoint, it doesn't have to be a line number. You can also specify a label. In other words, when execution reaches that particular label, stop. Okay? And we basically say, what this is saying is we put a breakpoint at the very first instruction of the entire program. So don't go anywhere, just stop right away. Because _start defines the starting point of the entire program. Okay, not a problem, put a breakpoint. Run the program, and naturally it will stop on the very first instruction. And this is the first instruction because I just commented out all the other instructions. So the instructions that you have to write, those were all commented. And this is the instruction right after what you guys have to deal with. But what I want to do is to say, okay, now how do I get back to these 3 bytes? What is the location of those bytes?
L1 minus X amount of bytes.
L1 minus X number of bytes. Now L1 is the address of the first byte of this dot long, right? So that means L1 minus 1 and L1 minus 2 will refer to this word, right? L1 minus 3, L1 minus 4 will refer to this particular word. L1 minus 5, L1 minus 6 will refer to these 2 bytes. Is that okay? minus 7, minus 8, minus 9. So this byte here should be at location L1 minus 9. L1 is just a label. What is a label? A label is nothing more than just a number, okay? And we can do arithmetic on numbers. Adding to it, subtracting from it, it should all work. Okay, so what we'll do is we'll take a look at that location. So the first thing, this is going to be very confusing, and that's why it's important to kind of pay attention. If you don't understand, you can watch it again. If I say print L1, it will give me something that is not correct, okay? It will display the correct location, okay? This is the right location, but it doesn't know what to do with it. Why not? But isn't L1 supposed to be a long, which is a number and stuff like that? In assembly language programming, there's no such thing as type. So L1 as a label is an address. But what is it an address of? There's no type. But tech, the code right there says this is the address of a .long. No, that's not what it says. It says L1 is the address of whatever is following. Whatever is following is 4 bytes that represents 223 as a value. But no one says that you have to look at all those 4 bytes at the same time. You can choose to look at only 1 byte or 2 bytes and stuff like that. So that's why this doesn't work. So print is not a good idea. Examine is a better idea. When you use examine or the X command, you get to choose how big of a chunk you're looking at. You can say B to say that each chunk is a byte. You can say H if you want to look at 16-bit as a chunk. I know it is W in the source code, but in the debugger, it is an H. If you want to look at 32-bit chunks, it is a W. I know in your code, W means 16-bit. In a debugger, W means 32-bit. It is very confusing, but this is the way it is. Okay, there's no way to get around this one. Okay, but let's look at everything as bytes, and then you can choose what base. Okay, you can say in hexadecimal, you can say in decimal sign, or you can say in binary. I personally think hexadecimal is the most convenient. Okay, so I would choose hexadecimal. Then you can tell you can tell how many of these things too. So if you want to look at 2 things, 2 chunks, each chunk is a byte, and each thing you want to print as a hexadecimal, 2bx will do it. So let's try this at L1. Is that correct?
Yeah.
Yeah, we just figured it out. This is good. Good stuff. What about printing 4 of these things? That's good. Okay. What about printing 8 of these things? Is that correct? Okay, let me show you the code again, because if you cannot see the next line is a 0x23, as a long, so that's correct. Okay, let's try to do a L1 minus something and see if it works. Okay, so we'll say L1 minus, I don't know, 6. There we go. Is that correct? Remember, before the label L1 definition, we have a whole bunch of dot word, right? And the first dot word is 34 as a base 10 number. Is that 34 in base 10? It's 2, 1, and 2 16s.
Yeah.
Okay, 2, 1, and 2 16 adds up to 34. That's good. This is the most significant byte of the dot word of the first dot word. The next one is 34 or 34 in hexadecimal, so it's just 34. And this one is 34 in octal, remember? And 34 as an octal number is 011 for the 3, 100 for the 4. You add 2 more zeros as the leading zeros. Then you chop it up in chunks of 4. This is one chunk, this is another chunk. 0001 as one chunk is 1 in hexadecimal. 1100 as one chunk is C in hexadecimal. So that's why we get that 1C. Is that okay? What if I do something like this? What if I give it a 3, L1 minus 9? We get 0C, 1, 2, and 0A. Is that making any sense? The first number is 1, 2 as a base 10 number, which is what we know as 12. C is 12. That's good. The second number is 0x12. In other words, it is hexadecimal 12. Okay, that's what we get. The third one is on the board already, at least earlier. I'm trying to find it right here. So 012 is an octal number. 1 as an octal digit is 001 in binary. 2 as an octal digit is 010 in binary. We've had 2 more zeros because we want to round everything to multiples of 4. And then we group these bits in chunks. 0001, excuse me, 0000 is one chunk. It gives us a 0 as a hexadecimal digit. 1010 as one chunk will give us A as a hexadecimal digit. So that's why we get 0A, and that's what we see on the projector. Are we still doing okay so far? Okay. If you can specify L1 minus 9, L1 minus 6, and so on and so forth in your program, in GDB, do you think you can use those as memory locations in a program? Well, otherwise it wouldn't be very useful, right? Okay, so you can use a label and then add something to it, subtract something from it in your code. So let me just kind of go back to your code and help point out which part we're talking about. So bunny.s. Okay, this is the only instruction where you can specify a memory location. Well, so it seems. But you also have to remember this thing here. Whatever you put into EAX is going to be used how? By the following instruction. How are we using EAX in the next instruction? It is serving as an address. So whatever you put into EAX better be a valid address. And how do we specify address again? A valid, useful address in this program. How do we use it? How do we specify it? The best way is to use L1 as an anchor, because L1 is the address of one of the bytes. So you basically use L1 as an anchor, and then you say, okay, do I want the byte or the 32-bit right there at L1, or do I want the byte or bytes that is before L1? If it's before L1, what do you do? L1 minus yada yada yada, right? If it's after, you say L1 plus, blah blah blah. Is that okay? Yep.
What if you overshoot? Yeah.
What if what?
You overshoot like minus 12.
If you overshoot, it will give you a segmentation fault, because none of the locations before the first dot byte is actually allocated to your process. So if you overshoot, it will give you a segmentation fault. Yep.
All right, so basically, like, just to get this straight, like, so the dollar sign's immediately gonna, like, if you're using the dollar sign is to specify a value to be stored into that, correct?
It is a constant. Yeah.
So basically, like, what you're gonna do is just like get some address location, just store that, like.
No, nothing to do with address. Whatever you specify after the dollar sign is the bit pattern that you copy to the destination. If you say $1, then 1 is copied. If you say $20, then 20 is going to be stored. Well, that depends on the base. Yes, but that's the bit pattern of whatever you specify after the dollar sign is going to be overriding the second operand. Okay? Just one more thing, okay? I know you guys are eager to go home and have your dinner, okay? I know I'm sounding like a Lieutenant Columbo. Do you guys even know who's Columbo?
No.
Really? Okay, so how many bytes have we allocated all together with all the dot byte, dot word, and dot long? We have 3 items on each line, right? So we have 3 bytes, 3 words, and 3 longs. 3 bytes is 3 bytes, 3 words is 6 bytes, 3 longs is 12 bytes. So how many bytes have we allocated all together? 21, very good. So here is the magic. Okay. The first location is L1 minus 9, because L1 is right in the middle of everything, but there are 9 bytes allocated before the definition of L1. So L1 minus 9 does define the actual beginning of everything. So you want to look at this and make sure that you understand why these are the bytes that are allocated. Okay, I would say this is the first step. The most important step is to understand this. Okay, look at this, look at the source code of the program, and say, can I explain why these are the content of the first 21 bytes of the entire program? That is the first thing you need to do. Is that okay? After this, then you can kind of move on and say, okay, so now what do I need to do to finish the homework assignment? It is kind of like a solving a puzzle thing. You kind of have to think about it from the perspective of restriction. Okay, you have to think about what instruction is the only one that can set these particular bits. If that is the only instruction that can set these particular bits, how do I lock it down? Where am I going to copy to get these bytes into these locations? So you have to think in those terms. Okay, it is solving a puzzle. There's no step 2, step 3, instruction here. You really have to kind of at least understand all of these things here, the instructions that we have talked about, and then try to solve the problem. All the steps that we have gone through in Logisim should also be helpful because each one explains what is really going on inside the processor. And we only have 3 types of instructions that we have gone through. Are there any questions? Okay, if there are no questions, I am going to stop the lecture. I will be over at the lab in case someone wants to start on this early, which is highly recommended.
Have a good evening.
Having 3 hours of lecture is a little bit tiring.
Yeah.
Roll sheet for 310 go around today or yesterday?
I did not pass the roll sheet of 310 today, I don't think. Yep, I forgot.
What about yesterday? I forgot to say it.
How
Would it
about
go around that?
I don't think I passed it around either.
Okay.